So Lewis structure tells us which atoms are connected to each other, but it really tells us nothing about the 3D geometry of the molecule. Now, there are two variables that define a molecule's structure. The first is bond length. Now, I want to remind you, bond length is just the average distance between the centers of two bonded atoms, and bond length will decrease across a row of the periodic table, and then bond length will increase down a column. So notice here, right, and I want to point this out, if something increases in one direction, it decreases in the other. So when we look at this, right, it will decrease in that direction. So bond length decreases across a row. So that means this, as we go across the row, this will have a smaller bond length. Then what we see is bond length will increase as we go down a column, and so we'll see as we go from, for example, HF to HCl to HBr, we'll have increasing bond length. Now, the second thing that determines the three-dimensional geometry of the molecule is bond angle. Now, bond angle, and we're going to talk about that more on this slide, bond angle determines the shape around any atom bonded to two other atoms. So to determine the bond angle and shape, right, count how many groups surround the atom. And what do I mean by groups? So when we talk about groups here, groups are either an atom, so another atom, or a lone pair, right? And so this is referred to as VESPR theory, or valence, shell, electron, pair, repulsion theory. And basically what it states is that, right, the most stable arrangements of the molecule will keep the groups as far away from each other as possible. And so VESPR is based on the fact that electron pairs repel each other. Right. And so you can see here, this is a summary table where if you have two groups, the geometry is linear and the bond angle is 180 degrees. My degree signs dropped off here for some reason. 3 groups is trigonal planar, it's 120. 4 groups is tetrahedral, it's 109.5. Now, if you are sitting here and you're saying, ooh, Dr. Pierce, I remember Gen Chem. We had more things like octahedral. You did, but we're not going to focus on those. This is what we're going to focus on. I want to give you a few examples of these geometries. So I want us to look at this atom right here. When we look at that atom, we see that there are 2 groups attached to it. There's a group here, the hydrogen, and then there's this, let me do it this way, this carbon group here. And so those are 2 groups that are attached to it. So it has a linear geometry, and bond angles of 180 degrees. When we come down here and we look at this carbon, we see that it has 3 groups attached to it. There's one group there, one group there, and then one group there. That is going to have a trigonal planar geometry and bond angles of 120 degrees. Now, if you look over here, you're going to see carbon. It's got 4 groups attached to it, and its bond angles are 109.5 degrees, and it has a tetrahedral geometry. Now, one of the things that I want you to notice is that we are going to start drawing in 3 dimensions. And the reason we do this is because molecules are 3-dimensional things, and we have papers and computer screens, and those tend to be 2-dimensional. So we have to figure out a way to try to represent something that's 3-dimensional on a 2-dimensional surface. So I want you to look at methane, and I want you to look up here at methane. And what we're going to see is we're going to see 2 bonds like we've drawn before, but now we're going to see a wedge here and a dash here, right? So when you draw molecules, what you're going to find is that the solid line, right, is used for a bond in plane. And what that means is that is kind of like sitting on your paper. So if you have your computer screen or your paper, it is sitting right there flush to that. Then what you're going to see here is a wedge. And the wedge, that is used for a bond in front of the plane. So that's kind of sticking out, like heading towards you. Then you are going to see a dashed line, right? And that's used for a bond behind the plane. So it's sticking kind of back behind the paper. This is as another representation here. Now, molecules can be turned in a lot of different ways, generating equivalent representations. And I know this is frustrating because you may draw this and your neighbor may draw this, and they're all of these are acceptable for methane. All of them are showing the same thing. I want you also to notice that when we look at these representations here, these representations are equal because what's happening here is the 2 hydrogens are really aligned with each other. And that's what we're seeing when we draw it this way. So it doesn't matter, right, whether the wedge or the dash is skewed to the left or to the right here. So if you see here, the blue is on the left and now it's on the right. It doesn't really matter one way or the other. Now, I've shown you a lot of examples of atoms being groups, and I want to remind you that electrons are also counted as groups as well. So when we look at this ammonia ion, what we see here is we've got a group here, a group here, and a group here for the atoms, but we also have a group here for the lone pairs. So there are 4 groups that surround that nitrogen. And so when you have 3 bonded pairs, right? So we have 3 atoms here and then 1 lone pair, that geometry is trigonal pyramidal. We also notice in water, one of the other geometries we're going to see is we're going to have 4 groups around oxygen, but there's 2 lone pairs and 2 bonded pairs or 2 atoms, and that's going to have a bent geometry. So what you're going to notice here is right? We just have really 5 geometries that you need to know. So far, you need to know trigonal pyramidal, you need to know bent, you need to know linear, trigonal planar, and tetrahedral. And those are really all that we are going to mess with as we go through organic chemistry. Now, I want to remind you of one other thing. What we see here is that as you add the lone pairs, you're going to see the bond angle decrease. So as we add lone pairs, the bond angle decreases. And so what we see here with methane is going to have 109.5 degrees, and then ammonia is going to have 107, and the water is going to have 105, because the lone pairs take up more room, and so they compress the bonded atoms together, reducing the bond angle.